Newton online homework. You should take a look at the homework problems in the chapter. And so just a quick survey. How many of you have been looking at these homework problems in the chapter? A couple of you. You're going to have to start doing this. I'm not going to be able to cover these each time that we do a chapter. You'll want to just take a look at these problems. Make sure that you understand, because Newton doesn't hit all the topics. Something to look at. So again, you have the answers to the blue problems, and so this doesn't take very long. And so your book will have problems at the end. For additional practice. So write the following numbers in scientific notation. Would the first one be in scientific notation? Actually, how many of you have finished these, chapter 3? Nobody? Okay, you'll want to stay on top of it, because next week, think about it, next week we have our test, chapters 1 through 5. Are you going to have enough time to study for that? So you need to plan early. A lot of people end up bombing the test. They just wait till the last minute. But, you have time to get started on these. Get some additional practice. Well, scientific notation, this is algebra. I'm assuming everybody had done these in algebra, correct? So we can just go through these quickly, just to reinforce. A, what's that in scientific notation? Yeah, 3.22 times 10 to the negative or positive 4? Negative 4. Yeah, the way I always remember scientific notation is, if you make this number bigger, which is 3.22 is going to be, then you have to make the exponent smaller, so it's going to be negative 4. How about this one? We're going to make this number smaller, so we've got to make the exponent bigger. So what would this one be? Yeah, this could be 6.03 times 10 to the 9, or, if this were an exact number, or it depends on how many sig figs we have. This is a little bit ambiguous. These are probably just placeholders, and so it's probably 3 sig figs, most likely. But if this were actually 10 sig figs, then we'd have to write 6.030000, all the zeros. It's unlikely because of what it's written. C, would that be in scientific notation? Just count out 3, 6, 9, 12. Yeah. 6.19 times 10 to the negative 12. So we're good. And then we got to go back and forth. So we take a look at look at number 3. Write the following numbers in ordinary decimal form. What would A be? A would be, 5,120,000. Are these? Let me know. Are these pretty basic? Would you say?
Yes.
Yeah. Okay. Then if it's really basic, then what you do is you just skip ahead. So we just skip ahead, and then, this way we can focus on the stuff that we need focusing on, and the stuff we don't need focusing on, we kind of just skim through. If this isn't, then there's lots of reviews for scientific notation online as well as elsewhere. something like this, you know, you just punch it in the calculator. So this is calculator practice plus sig figs practice. So whenever we have multiplication or division, the number of sig figs allowed in our final answer is based on the fewest number of sig figs in a given quantity. And so what we can do here is, let's go to the calculator. Let's take a look at the first one. The first one here is 7.87 times 10 to the 4th times 9.26 times 10 to the minus 8. So we'll just do 7.87 times 10 to the negative 4. Was it 10 to the negative 4 or 10 to the positive 4? Positive 4 times 10 to the positive 4 times, what was the other number? I'll tell you. The other number is 9.26 times 10 to the negative 8. 9.26 times 10 to the negative 8. So times 9.26 times 10 to the negative 8. 9.626 times. I screwed up the calculator entry here. So let me just do it one more time. 7.87 times 10 to the 4th. 4 times 9.26 times 10 to the negative 8. 9.26 exponent 8 negative. Yeah, different calculators do different things. And so here we can see our two numbers here. So we got 3 sig figs in this number here. 7.87 times 10 to the positive 4 times 9.26 times 10 to the negative 8. That gives us this 0.0728762. So we're allowed 3 sig figs, 3 sig figs. We're allowed 3 sig figs here. So we're going to have to drop the 7. If we drop the 7, I want you to show me that 7 that we're dropping. You know, so I see which digit you're dropping. And so the way I'd like you to report that answer is like this. We don't have to write all the digits out. You know, there could be 10 digits, there could be more. But it's critical that we write 0.00728 and then the extra digit 7 that we're dropping here. Even though, you know, after the 7 there's a 6. So after the 7, if there's a 6, should I round up the 7 to an 8? No, then we'll have that cascading, you know, domino effect of rounding. And so what we do here is you're going to show me the digit that you're going to drop, and then we'll just go ahead and round it to 0.00729. If I were to write this in scientific notation, what would it be? 7.29 times 10 to the negative 123. So we make this smaller, we'll make this number bigger. So 7. So that's something new. That is, we have to deal with the sig figs there, particular problems. So let's go backwards. Let's go back to here. So this is the same problem. You know, just entering it in the calculator. How many sig figs are we allowed in the final answer? 3. This one, that's just punching out more calculator practice. How many sig figs are we allowed in the final answer? 3. And then just more calculator punching. Then what you can do is you can check your answer to make sure you're keying it in correctly. A lot of people, when they key in scientific notation, you know, I see this all the time. Like they're not familiar with this key, the XP key. And so what I see a lot is this. Like if somebody enters this, they go 7.87, and then they hit the times, and then they hit this key, the 10 to the X key, and then enter the X value. That's a waste of time. You know, you should just hit this key. That'll take care of it for you. So make sure you do that. All right, let's take a look at continuing on here. Switching back and forth. complete the following operations. So we're just looking at the blue problems here. 6.18. Obviously, we're going through these, but what we do is, it's like this. This holds true for not just science, but other fields as well. So, for example, if you want to learn how to play, let's say, the piano or something like that, if you want to learn how to play the piano, do you just watch somebody play it, and then you just pick it up? I watched a 30-minute tutorial on how to play. Is that going to be adequate, do you think? No, and you would think that it's the same thing for this. If you watch somebody do these problems, they solve the problems, oh, that looks easy, right? And then when it comes to actually doing it on paper yourself, then it's a whole different story, So a lot of people, they kind of deceive themselves in going, oh, that's so easy, but it's like this path through the jungle. If you watch somebody who's solved these types of problems for many, many years, they know, which path to take. They know, don't go down that path because it's a dead end, or don't, there's some traps in this particular trap. They know what to look out for, but if you don't, then, you're going to be doing all these things, going down different paths, maybe dead end paths and that kind of stuff. So it's good to get practice, even if you've seen somebody do it. And so these are just division problems. Division, we just hit the division key rather than the multiplication key. So it's essentially the same thing. It's just sig figs. All these, if you look at all these are 3 sig figs. So it's not, it's just keying in and then just figuring out how to round it to the proper number of sig figs. So it's the same type of technique we did for the multiplication. We do it for this. So let's move on. So here we have a combination of multiplication and division. And so here, it's the same thing. Whenever we have multiplication and division, we look for the least number of sig figs. They're all the same, 3 sig figs. So this one's different, however. This one has 3 sig figs, 3 sig figs, 3 sig figs, and 2 sig figs. So in this particular one, we have to round the answer to 2 sig figs. It's the only difference here. So let's go ahead and do this one here. This is a little bit different. And so the problem is, I'll just read it off here off this sheet, but it's going to be 4.36 times 10 to the 8th. So the 4.36, the double E of the exponent times 10 to the 6th. Times 1.82 times 10 to the 3rd. So times 1.82 times 10 to the 3rd divided by 0.0856. 0.0856. I don't have to punch in this 0 in front here. We'll do it. Divided by 4.7 times 10 to the positive 6. 4.7 times 10 to the positive 6. So in this particular one, how would I round this number off? Well, probably the easiest thing to do, this is going to be 139,719.
Is it 4.36? Isn't it 4.7 or 0.7?
Oh, did I make a mistake? Yeah. All right, let me fix that right now. 4.7 times 10 to the 6. So I put 0. Let me see if I can just correct it here. See if I have backup. No, shoot. Copy and paste that. All right, let me redo that again. 4.36. Unfortunately, I can't use the keyboard either. 4.36 times 10 to the 8 times. Well, what's wrong with that number? Why is it giving me this? 1.36 times 10 to the 8 times 1.82. Did it again. Giving me this extra digit. Maybe this one's not so good. Let's try this one. 4.36 times 10 to the 8. Okay, times 1.82 times 10 to the third. Divided by 0.0856. Divided by 4.7 times 10 to the 6th. So we got, actually, we got 1,972,360. Okay, so 1,972,360. So usually I just carry extra digits when I initially write the answer. You know, I don't automatically round it on the screen because you want it written down. Usually, the reason I always write it down with extra digits is in case it's an intermediate answer and I need to do additional calculations with that number, or if I want to see, you know, if I rounded it down or rounded it up. And so, what would this round to 2 sig figs? What digit are we going to drop? We'll drop the 7, which is going to round this up. And so, if we round this up, it would round up to, yeah, it would just round up to 2 million, except this doesn't really indicate that. It's a little bit ambiguous. Is that 1 sig fig, 2 sig figs, or 7 sig figs? And so probably the best is to write this in scientific notation. So this would be 2.0 times 10 to the 6. Since, you know, since the answers are in the back of the book, we can just quickly check our answer. You know, just to make sure. Usually, what if the answer wasn't in the back of the book? You know, if the answer wasn't in the back of the book, then what I do is this. You know, first I'd look, does the order of magnitude sound about right? So I just do a quick check to make sure it looks reasonable. And so order of magnitude, this would be 10 to the 8 times 10 to the third is about 10 to 11. 10 to 11, this is 10 minus 2, so bring that up, that would be 10 to the 13 divided by 10 to the 6. It would be about 10 to the 7, so it's around 10 to the 7, which is ballpark where we are. So that's good because the coefficients are going to change things, you know. So this is 4 times 2 is about 8, divided by, I converted this, 8, this gives us about 1, divided by 5, which is 0.5, so half, 2. So this is ballpark, okay. Or we just check the answer in the back. And the answers are in the back right here. We just look at the answers. That was number 9, so we can go to number 9 here. Answers the blue numbered problems. Let's do a quick check on number 9 here. That was 9B. If we look at 9B, it's 2.0 times 10 to the 6. Basically it, so we're okay with that. So this is what you want to do when you got time. All right, let's continue on here. Now, number 11 is a little different. And so number 11 we should do because I didn't really do any of the sample problems with number 11. But so far, that was multiplication and division. For addition and subtraction, the rules are different. For addition and subtraction, when we're dealing with sig figs, we got to keep track of the number of decimal places. To keep track of the number of decimal places, we have to make sure that we're using the same. We either convert this to decimal form or we use the same. Like, so if this is 10 to the 7th, then we convert this one to 10 to the 7th, or vice versa. You know, we could leave this one at 10 to the 8th and convert this one to 10 to the 8th. But whatever we do, whenever we're doing addition or subtraction, these have to be the same or we get it in decimal. So we're going to do both. We'll get them in decimal, or we'll just get them at the same coefficient. So let's just take a look at this problem real quick. Just do that. So, .28 times 10 to the 6.38 times 10 to the 7. And so we just need to move the decimal 7 places. So 1, 2, 3, 4, 5, 6, 7. And so that gives us 63,800,000 plus 4.01 times 10 to the 8. So we'll move it 8 places. So it's 1, 2, 3, 4, 5, 6, 7, 8. And that gives us 401 million. And so we look at the number of decimal places allowed. And so I see here 6.38. You know, the decimal cutoff is here. Because 6.38, we just have 3 sig figs. These digits are insignificant. When I look at 4.01, the cutoff is here. And so what that means is that the uncertain digits don't match up. Here, the uncertain digit is this. That is the yes. So this is our drop digit, and this is our uncertain digit, the 8. 8 is our uncertain digit here, whereas the 1 is our uncertain digit here. And so having our uncertain digit here is going to give this, when we do 3 plus 1 here, it's going to be uncertain as well. And so what we have to do is we have to look at the uncertain digits here then, when we add this up. So let's go ahead and add these up. This is going to be 464,800,000. But let's figure out where the uncertainty is. So we have uncertainty in this 8. So the 8 plus 0 is going to lead to uncertainty here. And then the 3 is certain. However, the 1 is uncertain. So that's going to give us uncertainty in this digit here. How many uncertain digits are we allowed in science? We're only allowed 1 uncertain digit. So that means if we're only allowed on 1, we have 2 uncertain digits here. So we're going to have to drop 1 of these. And so that means we have to drop the 8. So we're going to round this to 465 million. And so in terms of scientific notation, that comes out to 4.65 times 10 to the 6, 7, 8 times 10 to the 8. All right, that's one way of doing this. The other way of doing it is to get them both the same. So what we'll do is we'll either get them both at 10 to the 7th or get them both at 10 to the 8th. Which way do you want to go? All right, we'll go 10 to the 7th. So we'll leave 6.38 times 10 to the 7th. Now, with 4.01, if we make the exponent smaller, so we're going to make it from 10 to the 8th to 10 to the 7th. If we make it smaller, then we have to make the coefficient bigger. So this is going to be 40.1 times 10 to the 7th. So we made this smaller, we make this bigger. Okay, now when we look at it again, the uncertain digit doesn't line up. You see the 8 here and the 1 here. Certain digits are different. And so what we're going to end up with is, again, 46.48 times 10 to the 7th, which is going to give us 2 uncertain digits, so we've got to drop one of those. We'll drop the 8. So this is
going to give us 46.5. It's 10 to the 7. And so we do it, the rule officially is this. We look at the decimal places. The one with the fewer decimal places is what we round to. And so this one has fewer decimal places, so we're only allowed one decimal place in this case. So we round to that.
And so this addition and subtraction here. All right, that was.
Would you put that back in the correct scientific addition, or would you leave it like that?
Well, it depends. You know, if this were one of the common ones like 6, 9, 12, I would leave it. But since this is not, then what I do is this. Because we use metric prefixes all the time, so I'd make this as 6. If I make this as 6, that's making this smaller. That must mean this goes bigger. And so this would be 465 times 10 to the 6th. And so the reason I would do it like that way is 465 million. It's easy. Or mega, 465 mega, whatever. The other option is to do it, you know, to 4.65. If I do 4.65 times 10 to the 8th, 10 to the 8th is not one of our standard prefixes. And so, you know, if you can't make it a standard prefix like this, in this case I'd just go here. And so both of these are acceptable.
In fact, you know, all of them are fine depending on. It doesn't have to be. I know scientific notation. They say take a number between 0 and 10. We don't always have to do that. We don't always do that. You know?
So the answer would be fine on the test.
Yeah, the answer would be fine on the test. The reason we don't always do that is because in science sometimes we don't like decimals. And so, for example, what's the diameter of a hydrogen atom, approximately? What is it? 100 what? 100 picometer. So the diameter of a hydrogen atom is 100 picometer. Well, a pico is what? A pico is 10 to the minus 12 meters. So it's 100 times 10 to the minus 12 meters. Is that correct? Yeah. But shouldn't this be written in proper scientific form? Shouldn't this be 1.00 times 10 to the minus? Okay, if I make this number smaller, then this has to grow bigger. So this is going to be times 10 to the minus, I made it 2. So this is going to be 10 to the minus 10 meters, right? And so really it should be 1.00 times 10 to the minus 10 meters. Well, how big is a hydrogen atom? Well, it's 1.00 times 10 to the minus 10 meters. Is that easy to deal with? No, it's a pain. And therefore we like it. Like this. Now, 10 to the minus 10 meters. This is what they're going to call archaic, or our book. Krakalici says that this unit is no longer good, but people use this unit all the time. This is kind of inconvenient, and so what they do is times 10 to the minus 10 meters is defined as an angstrom. And so there are two ways we can represent the size of a hydrogen atom. A hydrogen atom is going to be about 100 picometers in diameter, or it's going to be 1.00 angstroms in diameter. And so both of these are very common. So when the unit comes out funky like this, they just define a new unit here, because 10 to the minus 10 is not one of our convenient pico, nano, type micro units. And so this is defined. And it's specifically for meters. We wouldn't use angstrom for anything other than meters, 10 to the minus 10. And so angstrom, even though I know Krakalici says it's a unit that's going to be forgotten, it's not. People use angstroms continuously. And so when I learned the sizes of the atoms, all of them were in angstroms. And then we switched to picometers. It makes sense to switch to picometers, because if you switch to picometers, then we don't need this decimal point. And so atoms are going to range from 100 to
500, and so if it's 1.5, it's at 150 rather than 1.5, so we get rid of that decimal point, which is convenient too. And so the units are just a matter of convenience, what's easier to say. And so the same thing with scientific notation. The purpose of scientific notation is to make your life easier, not to make more rules. It's just to make expressing these numbers easier, so you figure out what makes sense, and then it's acceptable. Let's go look at conversion factors, section 3-2. Oh, the other problem was subtraction. So it's the same thing. For addition or subtraction, we've got to do it like this or this. So you can just try the subtraction and see if it works out. Let's move on to 3-2, which is conversion factors. What is the mathematical criterion for two quantities to be equivalent? That's a little bit... a little bit confusing. For one, what is a mathematical criterion? Mathematical criterion. So, something like that, we'd probably search out mathematical criterion because maybe it has a very specific definition, or maybe it's something very simple. Criterion. But, you don't want to spend too much time, right? This is just to get a rapid review. And so I wouldn't spend that much time. I'd see how they answered it and then see what type of context they're looking for, what type of answer they're looking for. And so that's number 13. I just go to number 13. Oops, you can't see it. Let me switch this over. And so this is the way I do this. I try not to waste too much time. So let's just see what the book says the mathematical criterion is. 13, they say two quantities x and y must be related in the form y equals mx plus b. Is that really the answer? Does it make sense to you? Well, everybody recognizes this equation. This equation is for a linear line, a straight line, right? But does everything have to be a straight line? No, there's things that are non-linear. One example of a non-linear thing is the electrical forces. We talked about Coulomb's law. In Coulomb's law, what happens is, does the force drops off with the distance, right? Does the force drop off linearly with the distance or non-linearly with the distance? So does anybody remember Coulomb's law? Force is proportional to what? Not gravity, not mass. Force is proportional, the gravitational forces, if we're looking at Newton. It's force is proportional to the charge on A times the charge on B divided by the distance. But it's not just the distance, it's the distance squared. So as the distance grows, then the force really dramatically drops. It's nonlinear. And so the force drops off dramatically with distance. And so that's nonlinear. This one, 13, I don't agree with. When we're looking at conversion factors, conversion factors are usually just straight. I talk about this because, with the temperature and the zeros didn't match, right? The zeros didn't match, so we didn't get a straight conversion factor. So we had to use the algebraic equations versus a regular standard conversion factor. A standard conversion factor is like this. where the zeros match. And so, for example, delta, delta X and delta Y. Let's say delta degrees C versus delta degrees Fahrenheit. If there's 0 degrees C change, let's say, you measure the temperature change. The temperature change today was 0 degrees C. That is, it's the same temperature as before. So today it was the same temperature as yesterday, let's say, in degrees C to the proper number sig figs. So if there's a 0 degrees C temperature change, what is the Fahrenheit temperature change? Is it 32? If it's 0 degrees C, isn't it 32 degrees Fahrenheit? True or false? If there's a 0 degrees C temperature change, does that mean the Fahrenheit temperature change is 32 degrees? True or false? False. False. That is, this is doing that thing. Okay, so if there's a 0 degree, there's no change. If there's no, then that means that in the Fahrenheit there's going to be no change too, right? The zeros match. So we can come up with a conversion factor like this: 180 degrees Fahrenheit for every 100 degrees C, which is equal to 9 degrees Fahrenheit for every 5 degrees C, which is equal to 1.8 degrees Fahrenheit per degree C. These are exact, actually. This is exact. And so it's exact. If we have 180 degrees Fahrenheit, it's exactly 100 degrees C temperature change. This is exact. Versus this. And this is where we need an equation like this. We need an equation like this if we're looking at the temperature. Let's say the temperature were 0 degrees Celsius. What is the Fahrenheit temperature? If the temperature were 0 degrees Celsius, the Fahrenheit temperature would be 32 degrees because the zeros don't match. And so we have different criterion here. This is the conversion factor proper. This is algebraic equation. Algebraic equation is not what we call technically conversion factor. This is an equation to convert from one temperature to the other. But the zeros don't match. This matches because we're talking about delta T's here. This doesn't match because we're talking about T's here. And so when we're talking about conversion factors, the zeros match. So for example, let's look at some conversion factors here. So we know this one, 1 inch for every 2.54 centimeters, or 2.54 centimeters for every 1 inch. Right? And so this is a conversion factor proper. This allows us to convert. This one allows us to go from inches to centimeters. So this converts inches to centimeters. Centimeters to inches. Sorry. This converts centimeters to inches. This one converts inches to centimeters. So we use these, just flip it over. Here, if I have 0 inches, how many centimeters do I have? If it's 0 inches, I have how many centimeters? 0 centimeters, right? And so the zeros match. And so this is our standard conversion factor. It's just when the zeros don't match, we have to switch to the algebraic equation like this. This is temperature degrees C is equal to 9/5 temperature degrees Fahrenheit is equal to 9/5 temperature degrees C plus 32. That's not what I call a conversion factor. These are what I call conversion factors here. These are conversion factors that we use. Okay, we have two types of conversion factors. We have exact conversion factors and we have approximate conversion factors. And I ask you to memorize, is this one exact or approximate? This is exact. How about this conversion factor? 3.785 liters per gallon. Is that exact or approximate? This is approximate because we rounded it to 4 sig figs. So the way we read this is this: 1 gallon, exactly 1 gallon is approximately 3.785 liters. Right? Etc. And so the criteria, what I was thinking, and what I was thinking is completely off from what they were thinking. What I was thinking as far as mathematical criterion for equivalent
what was the original question again? The original question was this. What is the mathematical criterion for two quantities to be equivalent, right? What I was thinking, when I read this problem initially, I was thinking they were talking about exact versus approximate. And so I was thinking, in a criterion like this, these are exactly equal by definition, versus a conversion factor like this is approximate because we round it. We don't want to use all the digits. It's inexact, it's a measure. And so what I was thinking was the difference between an exact conversion factor versus a measure conversion factor. Measurements always are going to be approximations of it because measurements, can you measure something exactly to an infinite number of sig figs? No, it's not possible. So measurements always contain uncertainty. And so I didn't, sometimes that happens, the answers are kind of, I'll keep that. 15, let's move on. Well, here, let's look at 14. This is the sister problem. All these problems are paired. 60 seconds and 1 minute are equivalent quantities. Explain why this is true. It's by definition. There's no explanation, right? It's defined. 60 seconds is defined as 1 minute. 1 minute is defined as 60 seconds, correct? And so that's exact. Let's see what the book's answer says for actually there's no book's answer because this is number 14. But how would you explain this in terms of y equals mx plus b? If that's the mathematical criterion, how does it fit y equals mx plus b? Well, b, maybe b is 0. I mean, if you have 0 seconds, you would have 0 minutes. So. And then we might come up with this, like we did for the temperature. We could come up with an equation, but it doesn't make sense the way we do things mathematically. And so the equation we might come up with is we go from 0 to 1 minute, and we go from 0 seconds to 60 seconds. But this has to be defined first. So we have to know this definition originally. And then y is seconds. But anyway, I think we're getting off track here. So let's not even bother spending any more time with that particular problem. If there's a question like that, ask me in class, what they're talking about. Okay, write the equivalency in both conversion factors for each relationship. 10 dimes is $1. All right, 10 dimes per dollar, $1. Or we write it $1 per 10 dimes. And so we always write two conversions. This converts dollars to dimes, because we cancel that out. But it depends, because sometimes we cancel out the numerator. I'll show you an example of where we cancel out the numerator. In our standard way, dollars to dimes, this one converts dimes to dollars. A football field is 100 yards long. 16 ounces is 1 pound. All those are measured or by definition? All those are by definition, so all those are exact. We just come up with a ratio. Conversion factors are just a ratio. Now, conversion factors can be multiple things. So we could have something like this. We could have 4.18 J or G degrees C. J, this stands for joules. We'll talk about joules later. Joules is the unit of energy per gram per degree C. This is how many joules it takes to heat 1 gram of water by 1 degree C. But this one, it converts from grams and degrees C to joules, etc. And so we would need to multiply this by two things. We need to multiply this by the mass in grams,
And we need to multiply this by the temperature change. Actually, this is going to be a temperature in degrees C. So this is a temperature change. And so we come up with this equation. This equation that people memorize, but it's just based on dimensions. The grams cancel, the degrees C cancel. And so this thing's called C. This is called M. And this is called delta T. And so people memorize this as, it's easier to say Q, this is the energy in joules, which you call heat. Q is heat. And so Q is equal to, people memorize this in Chem 4 as MC delta T. And so a lot of these equations that we use in chemistry and physics just comes from just canceling out the units. You know, what do we need to cancel out grams? We need the mass. What do we need to cancel out the degrees C? We need this. And what are we left with? We're left with that. So that equation will come from dimensional analysis.
How long will it take to travel the 406 miles between Los Angeles and San Francisco at an average speed of 48 miles per hour? Well, let's take a look at some of these here. So we have 406 miles, and then we have 48 miles per hour. So 48 miles per hour. Miles will abbreviate MI, hour is H/R. So 48 miles per hour. And so this is just a standard dimensional analysis problem, number 21. Actually, maybe I should do the black ones, but it doesn't matter because you just repeat these ones. And so we go 406 miles, and then we need to get rid of miles. So the relationship would be 48 miles for every hour. How many hours this would take. And so just punching it out in the calculator, what do we have here? I'll just do it on this one. So 406 divided by 48. Comes out to, now I carry extra digits, 8.4583. I mean, usually I carry way more digits than I'm allowed. But I'm not going to carry all of them because my calculator is showing 3, 6, 9 digits right now. So it's way more than we're allowed because we're only allowed how many 6 digits? Two 6 digits. So we just say 8.5 hours. Now, you can't forget the units. The units are important. Units are going to be at least half the problem. Don't forget units. So 8.5 hours. So we just string along. We did some more challenging dimensional analysis problems, but these are just straight single conversion ones, just to get you some more practice. All the more challenging ones are, you know, we don't want to end up at hours. So for example, a more challenging problem would be how many seconds would it be? You know, so we go from hours to minutes and then minutes to seconds, that kind of thing. And so those are typically the more challenging problems, is just stringing along. And sometimes they can be much more challenging. So how many minutes does it take a car traveling 88 kilometers per hour to cover 4.3 kilometers? Well, let's do a more challenging one here. And we don't always convert the numerator. Sometimes we convert the denominator, and sometimes we want to just make a conversion of some ratio like this. And so if we have 88 kilometers an hour, this would just be this is a typical question. How many miles per hour is that? Well, actually, this one would be a straight type of problem, but we have two choices here. One, we could just look up in the book. We can go from kilometers to miles. We look that up in the book. Our book will have it, I'm sure, our book has this one. You can take a look and see. So this is the inside front cover of the book. It has a bunch of useful constants here. We'll just go down to length. Does it? No. Maybe our book has it in the chapter. And so we look in the chapter for it. It'll probably take some time for me to find it. Or we could just look up online for it. So we look up. Unless, do you know it already? The conversion from kilometers to miles. Actually, I do it the other way. So I go from miles to kilometers, 1.6. Let's see what I'm doing here. All right, so 1 mile is equivalent to 1.6 kilometers. So I could do that. But,
You know, how many sig figs do we have here? 2. And so in this conversion factor, I want to use how many sig figs? Minimum of 2, but ideally we should use 3. And so what conversion should we use? We should use 1 mile. Exactly 1 mile is approximately 1.61 kilometers. That's to 3 sig figs. Okay, this way we minimize what? We minimize rounding errors. But I wouldn't have done it this path. I would have done it a different path. You know which way I would have done this? Because, you know, just gaining a little bit of experience with this. I would have went from kilometers to, somebody tell me a different path we could have used to solve this without having to look this up. Maybe. I wouldn't have had to look this up because I should have been able to do this from memory. And so I would have gone from kilometers to, well, where can you go from kilometers? Kilometers to what? To meters. I would have went from kilometers to meters, meters to well, kilometers to meters, that's that one, you know, because there's going to be 1,000 meters for kilometer. Is this approximate or exact? Exact. Then I would have went from meters to well, where can you go from meters? You could go from meters to kilometers. You can go from meters to meters to feet. Do you have that one memorized? Okay. What do you have memorized? Maybe kilometers to meters. We can go from meters to micrometers. Is that good? We go from meters to nanometers, meters to megameters, meters to, we can go from meters to centimeters. That's exact. There are 100 centimeters exactly in a meter. That is exact. Okay, then from centimeters, we can go to where? To inches. If we go from centimeters to inches, well, that's exact too. There are going to be 1 inch is equivalent to exactly 2.54 centimeters by definition. And then inches to feet, because we know that there's exactly, in 1 foot, there's exactly 12 inches. And then we can go from feet to miles. Now, did you memorize this one? Yeah. 1 mile is exactly 5,280 feet. So these are all exact conversion factors versus this one. Which one's going to give you a more accurate answer? The top one. So I would have gone with the top one, even though it's more work. I would have had less rounding error there. And besides, I wouldn't have to look it up, the conversion factor, because most people have it memorized the 2 sig figs. But 1 mile is 1.6 kilometers. But, you know, the 3 sig figs, how many of you had it memorized, the 3 sig figs or 4 sig figs? Probably nobody. So, okay, just some more basic ones, minutes and seconds, inches and feet, dollars and seconds.
You know, if you find you need more practice, you know, try the other problems, the black ones as well. What you want to do is you want to find out where you need some additional help. And so here we come up to 3-3, strategy for solving quantitative chemistry problems. The strategy is, oh, actually we already did this. The strategy is using, what's this technique called? This is called dimensional analysis. So just work on these. Most of these are just one conversion. You know. How many weeks are in a decade? The decade's 10 years, right? You go from there. Okay, then we go on to 3-4, introduction to measurement. List at least 2 measurements that would be routinely made in a healthcare clinic. One is temperature. The other would be blood pressure. Are those exact? Do you get your exact body temperature? No. All measurements are going to be approximate. Blood pressure is not going to be exact, you know, to the number of 6 days. All measurements have uncertainty. All right, let's go on to metric unit. A woman stands on a scale on an elevator in a tall building. The elevator starts going up, rises rapidly at a constant speed for half a minute, then slows to a stop. Compare the woman's weight as recorded by the scale and her mass while the elevator is standing still during the starting period. So what's going to happen as the elevator accelerates? What's going to happen to their weight? As it's going up, are they going to weigh more or less? Yeah, going down the elevator, they would probably weigh less, but going up the elevator, they're going to weigh more. You should feel more pressure on your feet going up the elevator, less pressure on your feet going down the elevator. That pressure, that's additional force, and so their weight changes. But what about their mass? You know, so the pounds will change, but the number of kilograms that person weighs doesn't change. Mass is not going to be impacted by force like that. What is the metric unit of length? Just mentioned it. What is it? Meter. Kilobuck is slang expression for a sum of money. How many dollars is a kilobuck? 1,000. A megabuck? Million. 1 milliliter is equivalent to how many liters? 1/1000 liter. Which unit, megagrams or grams, would be more suitable for expressing the mass of an automobile? Megagrams. You know, a gram is a very small unit. Makes sense. Okay, make the conversion centigram to grams. A centi is, yeah. In other words, there would be 100 centigrams in a gram. Kilograms to grams, centigrams to milligram. Centigram to milligram, we would do it, you know, this is the way I do it. So let's take a look at number C. Where? So if we go from, let's just look at the units here. I'd go not from centigrams to milligrams. I would go from centigrams to grams and then grams to milligrams. And so centigram to gram, we would just say 1 gram has 100 centigrams, just like 1 meter has 100 centimeters. And then from grams to milligrams, then we know there's 1,000 milligrams over gram. So these are the key conversion factors. We just string them together. These are exact conversion factors. And I go 4.54 times 10 to the 8 centigrams. You know, there are different ways we could do this. You know, we could punch it in the calculator, or we could just do this. You know, this is 10 to the minus 2. This is 10 to the minus, or 10 to the positive 3. So 10 to the minus 2, 10 to the positive 3. This is 10 to the positive 1. So this would be 10 to the 9. 4.54 times 10 to the 9 milligrams. Okay, this is more unit conversions here. Less common units. Less common units I don't even bother. Except this, hectogram to gram. You guys forget that one. Meter to picometer. Picometer is very common. I don't know why this is less common. This one I don't even know what it is. All right. These ones I wouldn't even bother. That's very. I'm going to use it. Nanometers, meters. Nanometer is very important. So this is where gigagram to gram, maybe. Megameter to centimeter, maybe. Do those. It's just string one conversion factor. Okay, let's take a look at some measurements here. So we're looking at this fluid, and this is kind of tricky here, because this is very funky looking. What this curved surface, what it's called? This name for this curved surface is called meniscus. And you see the liquid is trying to crawl up the sides of the container. And that tells us that the liquid loves glass. Otherwise, it wouldn't crawl up the sides like this. But anyway, if the liquid crawls up the glass, it's better from the top or the bottom. The bottom. And so it looks like the bottom here lines up with this line right here. And so let's do a little bit of practice measurements. And so I need to see what you guys are, or how you guys are reading this. So I want you to record your answers here, and then we're going to reflect them and make sure people are reading. If there are extras, can you pass them out? Is there an extra? Yeah, okay, this will be number 51. Can't turn off the lights, right? Number 51, what is that measurement? What's the volume of the liquid? This is in milliliters, so the units would be ml. A lowercase m, capital L, like this over here. So what is this measurement? And so I see this, I'm looking at this, and it's lining up with this line right here. So write that, this is 51A. Okay, then we're going to go to 51B. 51B, let's look at how this lines up. We're going to say that this one lines up with this line here, right on that line. So if this one is right on this line, what is it? 51B. It looks like both of them match up with the line that's marked there. So go ahead and do 51A, go on to 51B. Tell me what that measurement is. Did you have enough time? Okay. 52A. What is the length of this beam? Like the end, I look at the end here, see how it matches up here. The end of the leaf is right about here. So what is that? This is in centimeters. Is that inches? Oh, it's centimeters. How do I know it's centimeters? Look at the bottom one.
instructions, it says it's calibrated in inches.
Oh.
The ruler is calibrated in inches.
Calibrated to inches. All right. Sorry. How many marks do you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've never seen an inch scale that's not marked an 8th or 16th. Have you? Anyway, it's all right. We're going to do it in inches. It doesn't matter. Just the number is what I'm after. So what is this one here? So if we look at this one, we're going to make sure. So, you know, that, what I just did there shows bias, you know. You have to be careful because sometimes you'll have a bias about how things are supposed to be, and that can cloud your measurement. And so I went in there with a bias thinking it's going to be in centimeters because I look at this one. And, can you guys see where it lines up? Yeah, this should make this a little easier here. Looks like it lines up just to the right of this one right there. But anyway, why don't you go ahead and just eyeball that. Okay, are you guys done? Go back to the, which one? The other one? This is the same lead. Okay, what we'll do is we'll take a break now, and then I'll collect the cards. So let's take a